In this video, we'll learn about integrator and differentiator circuits made from op-amps. We begin by considering a generalized inverting configuration, where the resistors R2 and R1 from the inverting configuration have been replaced by impedances Z2 and Z1 that can be composed of any combination of resistors, capacitors, even inductors. The analysis of this circuit is very similar to that of the inverting configuration. If we assume an ideal op-amp, we've got a virtual ground here, which gives rise to a current VI, flowing the other way, VI over Z1. Since there's no current going into the op-amp, that current flows through Z2 and gives rise to a voltage drop VI over Z1 times Z2. So therefore, the output node VO is simply equal to negative that voltage drop Z2 over Z1 times VI. Hence, the gain of this generalized inverting configuration is negative Z2 over Z1. Now we can make use of reactive components to form those impedances Z1 and Z2 and give us a response that's frequency dependent. And we're going to do that to realize differentiators and integrators. Here's the basic integrator circuit. Its operation can be understood in the time domain, recognizing that the input current I1 is simply equal to VI over R, assuming our virtual ground here at the negative op-amp terminal. That current all flows into the capacitor C and is therefore integrated on it. So VC is the time integral of the current I1 onto the capacitor C. Substituting in for I1, we've got VC being the time integral of the input voltage. So the output voltage is simply negative VC. And that's the expression shown here. Now, you'll notice that here we have placed the lower limit of integration at somewhat arbitrarily at time t equals 0. And so the assumption is that at time t equals 0, the capacitor C had an initial voltage across it equal to VC. We can also analyze this circuit using a phasor analysis. Just substituting into the analysis from the previous slide, the impedances Z1 equals R and Z2 equal to the impedance 1 over SC of the capacitor. Substituting those values into the expression from the last slide gives us a circuit response of negative 1 over S RC. We can plot that frequency response here. Shown here is the magnitude response. As we would expect from an ideal integrator, we observe that the magnitude response is infinite at DC, which on a log scale here on the frequency axis would be way off to the left, and that the magnitude response decreases with a slope of 6 dB per octave or 20 dB per decade. it reaches a magnitude of unity, or 0 dB, precisely at the frequency 1 over CR. And you can see that straightforwardly by solving for the frequency where the magnitude of this expression is equal to 1. We'll refer to that as the unity gain frequency of the integrator. This exercise asks us to design an inverting integrator with a specific input resistance and time constant. So here's our integrator circuit. We call it a negative or inverting integrator because, as we saw from the last slide, the output voltage is actually negative the time integral of the input voltage. We can see, assuming an ideal op-amp, since there's a virtual ground at the negative op-amp terminal, the input resistance here is simply equal to R. So when we're asked to design the circuit to have an input resistance of 10K, we immediately know that the resistor value R must be 10 kilo ohms, because that's the input resistance of this configuration. We're also told the integration time constant. The time constant is the product C times R, or 1 over the unity gain frequency of the integrator. We're told that that's a millisecond. Rearranging, we can find the missing capacitor value, 10 to the 3 over 10 kilo ohms, which is 10 to the 4 ohms. That means the capacitance value is 10 to the minus 7 farads, or 100 nanofarads. And that's it. Now, the fact that the integrator circuit has infinite gain at DC can cause us some practical problems. So instead, a common modification is shown here, where the capacitor in the feedback network is placed in parallel with a resistor R2 that limits the gain at DC. We'll see how as the analysis here proceeds. First, let's recognize that this is still a special case of the generalized inverting configuration, where the impedance Z1 is simply the resistor R1, and the impedance Z2 can be written as 1 over its admittance, and the admittance of the parallel combination of R2 and C2 is simply the admittance of the capacitance C2 plus the admittance of the resistor R2. You can rewrite this as R2 over 1 plus SC2 R2. So now that we've got the impedances Z1 and Z2, we can substitute that into our generalized inverting configuration expression, negative Z2 over Z1, and we find that we've got this expression here, negative R2 over R1 in the numerator. That's the familiar result we get from any inverting configuration with just resistors. And then we've got the frequency dependent term in the denominator. So this expression, again, gives us a familiar result if we consider what happens at DC. At DC, we can find the result by substituting in S equals 0 into the expression we just derived, in which case the denominator becomes unity and we're just left with negative R2 over R1. Now this is satisfying since it's the exact same result we would have got by considering the circuit schematic directly at DC. At DC, we could neglect this capacitance as an open circuit and we'd simply be left with the inverting configuration with a gain of negative R2 over R1. So that's good confirmation that our analysis is correct at DC at least. And what happens at high frequency? Well, we can consider that by looking at what happens when omega goes to infinity and replace S by j omega in our analysis over here. In that case, the unity term in the denominator would become insignificant compared to the other term. So we'd be left with a gain expression that's negative R2 over R1, and only the second term in the denominator would remain. The values of R2 would then cancel, and we'd just be left with negative 1 over S C2 R1. Again, this is satisfying because at very high frequencies, we would expect this capacitance to have a much higher admittance than the resistor R2. So therefore, we could neglect the resistor R2 as being approximately an open circuit compared to C2, and we'd then just be left with the simple integrator, and we get a result that's exactly the same as that for the simple inverting integrator. So with this intuition, we can create a rough sketch of the magnitude response. We're going to sketch it here on a log scale with respect to frequency omega, and on a linear in dB scale with respect to the magnitude of V over VI. Now we said that at DC, we're expecting a magnitude response of negative R2 over R1, but that at high frequency, we expect it to behave just like an integrator, where the magnitude response rolls off with a slope of 20 dB per decade and reaches a unity gain frequency at 1 over C2 R1. So a key feature that we're likely interested in is what's the frequency around the transition between these two. And we'll call that the corner frequency, where the magnitude response bends down. Now, in fact, we could find it geometrically from this sketch, but instead let's find it analytically. And we're going to do so by finding the frequency at which this denominator here becomes equal to root 2. And that'll happen when, with S equal to j omega for physical frequencies omega, we've got the magnitude of the second term in the denominator equal to unity. That is where SR2C2 equals j omega R2 C2, and where that is equal to unity, that's going to give us our corner frequency. Let's call it omega C. So simply rearranging that, we find that we've got a corner frequency of 1 over R2 C2. So in summary, we've got a DC gain that depends on the ratio of R2 over R1, a corner frequency that depends on this network here, and then an integration time constant that depends on these two component values. This circuit is sometimes called a lossy integrator. Because compared to an ideal integrator, we've got some loss of gain at low frequencies. Or another way to think of it is that rather than all of the current through R2 being integrated onto C2, some of that charge is lost through the parallel path provided by a resistor R2. It's instructive to think of how the integrator and lossy integrator differ in their response to ideal pulse inputs. So the integrator is shown here on the top, and the output in response to this rectangular pulse shown here would be just as we would expect. Remember that it's a negative integrator, so when the applied input is positive, the output voltage goes down. And then when the applied input voltage returns to 0 volts at time 1 millisecond, then beyond that, the output is held constant at whatever value it integrated up to. By contrast, let's think about what happens with the lossy integrator. It doesn't perform a perfect integration when the input is at 1 volt here. Instead, what it's really doing is exponentially settling to its DC gain, which for this configuration is negative RF over R. For the values specified, if we've got a DC gain of negative 100, then that means that what we've really got here is not a straight line, but a gentle curve that represents exponential settling to a value of negative 100 volts. And the time constant of that settling is equal to our integration time constant. C times RF. So in this case, the integration time constant is very slow, so it looks almost like a straight line, but it's not a perfect straight line, and that's the difference between the lossy integrator and the ideal integrator shown at the top. For the lossy integrator, when the input returns to 0 at time 1 millisecond, then the output begins exponentially settling back to 0 volts, because that's what you get when you have a 0 volt input through a DC gain of negative 100. Again, the time constant of settling here is determined by the product C times RF, which may be very slow. So it may take some time to settle back to 0 volts, but it doesn't hold the output constant the way the ideal integrator does. Again, that's why we think of this as a lossy integrator. That charge is being lost. In fact, what's happening is the charge that was built up on the capacitor C is slowly discharging through the resistor RF when the input VI is equal to 0. Shown here is a differentiator circuit that's made very similar to the negative integrator shown before. Again, you can use the ideal op-amp assumption to assume a virtual ground at the negative op-amp terminal, and then we see that the current I that flows through the capacitor is the time derivative of the input voltage VI. That current's got nowhere to flow other than through R, so it produces a voltage at the output that's proportional to the time derivative of the input. This could also have been found by a straightforward phasor analysis where the impedance Z1 is 1 over SC, and Z2 is equal to R. In that case, the ratio of negative Z2 over Z1 would give us negative SCR. The frequency response, as we expect, is obtained by substituting in S equals j omega, and we see that its magnitude is proportional to frequency omega. So when we plot it with dB on the y-axis and a log scale on the x-axis, we find that it increases at a rate of 6 dB per octave or 20 dB per decade. Finally, by equating this magnitude, the magnitude of the frequency response to unity or 0 dB, we find the unity gain frequency is equal to 1 over CR.